Welcome to Advanced Foundation Maths lecture series. In this lecture, we will cover Chapter 7, Set Theory. So let's get started. So set is defined as a collection of well-defined elements. A set is generally denoted by capital letters. For example, set of natural numbers is denoted by capital N, set of whole numbers is denoted by capital W, and so on. So there are two methods to write a set. So first method is called the listing or roster method. In this method, we list down all the elements of the set within curly brackets. For example, set of natural numbers is denoted by capital N and we write it within these curly brackets. So natural numbers are 1, 2, 3, 4, dot dot dot. These are called elements of set N. Similarly, set of whole numbers is denoted by capital W and which can be written as curly bracket 0, 1, 2, 3 and so on. Similarly, set of integers is denoted by capital Z or capital I, which is equals to all the integers positive, negative, which are possible. So this is the first method where we write down all the elements. Now next method is the set builders method or the rule method. In this method, we define a set by some condition or by some property, and it is written as curly bracket x such that some rules will be given like rule 1, rule 2 and so on. So let's say we need to write set of all even natural numbers in set builders method. So if we need to write in roster method, we would write 2, 4, 6, 8 and dot dot dot, where we list down all the even natural numbers. Now let's see how to write in set builders notation or set builders method. So we write curly bracket x such that x equals 2n, where n belongs to natural number. So essentially we take value of n as let's say 1. So we get x as 2 into 1, that's 2. So when we take n as 2, we get x as 4. When we take n as 3, we get x as 6 and dot dot dot. So this set has the values of x which are 2, 4, 6, 8 and dot dot dot. So this is the set builders method. Now we can also represent set of even natural numbers as curly bracket 2x such that x belongs to natural number. So when x is 1, we have an output 2. When x is 2, output is 4. When x is 3, this is 6 and so on. So this is set builders notation. Now let's do few questions. So write the following set in roster form. So first is a equals x such that 2x plus 3 equals to 15. So we need to write that value of x which satisfy this condition or this rule. So we can solve this. We will get 2x equals to 15 minus 3, which is 12. So x would be equals to 12 by 2, which is 6. So this would be equals to just one element, 6. Now next is b equals to x such that x square equals x. So all x which satisfy this condition would be the part of set b. So x square equals x. So we can bring x on the left side. So we will get x square minus x equals 0. So this implies x minus 1 would be equals to 0. So now since the product of these two is equals to 0, therefore either this x equals 0 or this equals 0. So therefore either x equals 0 or x equals 1. So therefore set B would contain two elements, that's 0 and 1. Now let's do the third part. C equals x such that 5x minus 10 equals 0 and x square equals 16. So whichever x satisfy both these conditions would be the part of set C. So 5x would be equals to 10. So x would be equals to 2. Simultaneously, x square equals 16. So therefore x equals plus minus 4. Now there is no value of x that would satisfy both these conditions, meaning x cannot be simultaneously 2 or plus minus 4 and plus minus 4. Therefore, this has no elements. Now we'll see later that this is called an empty set or a null set and is denoted by the symbol phi. Now next is d equals 4x such that x belongs to natural number. So therefore, we keep substituting x as 1, 2, 3 and we'll keep getting the elements of set D. So when we substitute x as 1 we get 4. When we substitute x as 2 we get 8. When we substitute x as 3 we get 12, 16 and dot dot dot. So this is the element. So these are the elements of set D. Next, let's have a look at few terminologies and the different types of sets. So first is the cardinal number of a set. So if let's say I have a set of vowels A, E, I, O and U, let's denote this as capital V. So V set is the set of all vowels. Now if someone asks us what is the cardinal number of V, so it is denoted by n of V and that is equals to the number of elements present in that set. So n of V would be number of elements in this set, which would be 5. Next is a null set. Null set is also called an empty set. It does not contain any element, or we can say it has 0 elements. It is denoted by the symbol phi. This is read as phi and can also be written as 2 brackets. Now note that when you write bracket and phi, this is not a null set. It has an element which is phi. In fact, the cardinal number of this set is 1. However, cardinal number of null set is 0. An example of null set is x. X not equals to x. Now elements of this set would be such elements which is not equals to itself. Now tell me, will 2 be part of this set? No, because 2 is equals to 2. It is not equals to 2. So therefore, if you realize, this is a null set because there is no element which would satisfy this condition. We can write this as phi. Now singleton set is a set which contains only one element. So for example, if I write a set and just write one element, let's say E, so this is a singleton set. Finite set is a set containing finite number of elements, like set of vowels, because it has 5 elements, which is finite. Infinite set is a set containing infinite number of elements, that is, cardinal number of such set is infinity. So for example, set of natural numbers n has elements 1, 2, 3 and we write dot dot dot. Now this dot dot denotes that it keeps going on. So how many elements does it have? It has infinite number of elements. So this would be an example of infinite set. Equivalent set are sets which have the same cardinal number. So for example, if I write A equals to 1, 3 and B is another set which is P, Q. So these two are equivalent sets because the number of elements in both the sets are equal. Two sets are said to be equal sets if they have exactly same elements. So for example, if I have A equals to 5, 10 and then 12 and let's say I have B equals to 10, 5 and 12. Now A and B have exactly same elements, so these would be equal sets and we can write A equals B. Universal set contains all possible elements which occur in the discussion, meaning it is the superset of all possible. Now next is subset. A set A is said to be a subset of set B if all elements of A is present in set B. So it is symbolically written as A is a subset of B. So this is the symbol used to represent A being a subset of B. Now let's see an example. So let's say I have a set 1, 2. Let's write all the possible subsets of 1, 2. So first of all, keep in mind that subset is also a set. So one subset of this can be this one, meaning a set containing element 1. If you notice, all elements of this set is contained in this, so therefore this is a subset of this. Similarly, this is also a subset of this. Now, if you realize 1 comma 2, this set is also a subset of this because all elements of this is contained in this. So theoretically, this is also a subset. Similarly, an empty set is also a subset of this set because all elements of this is present in this. Now remember, the rule is all elements of given set must be present in this set. Now since there is no element, so therefore this will also qualify as being a subset. Now similarly, this set A, B and C, let's write down all the subsets which are possible. So A, then B, and then set C, then A comma B, B comma C, and then C comma A, and A, B, C, and null set. So all the subsets of A, B, C possible are these. Now, if you notice, every set is subset to itself, meaning this is subset to this and this is subset to this. Empty set is also a subset to every set. So empty set is subset to every set. Now next is the total number of subsets of a set containing n elements is, so let's count how many elements these are. So these are 4 elements. These are 8 elements. So how do you get the total number of subsets is by using little bit of permutation and combination. So let's say I need to form a set using these 3 elements. So I have 2 choices for the first element, either I select it or I don't select it. I have 2 choices for the second one and similarly 2 choices for the third one. Now we multiply all of these because we need to make a choice for all of them at the same time. So the answer would be 2 cube, which is 8. So there would be 8 subsets possible for this, which is this. So total number of subsets of a set containing n elements is 2 to the power n. Because if you have n elements, each element will have 2 choices and we multiply them to get 2 to the power n. Now second thing to notice that the set itself and the empty sets are called the improper subsets. So essentially this null set and the set itself are called improper subset. So similarly this would be improper and this would also be improper subsets, and the remaining would be the proper subsets, meaning these two are proper subsets. Similarly, these 6 are also proper subsets. Now next is power set of a given set. It is the set of all possible subsets of the given set A, and it is denoted by capital P of A. Let's say we need to write down the power set of A equals 1, 2. So the approach here is that first we write all the possible subsets of this. So first set would be a null set, second would be this, third would be this, and then fourth would be this. Now the set of all subsets, meaning set of all these subsets, is called the power set of A. So this would be the power set of A. Now let's say we need to find the power set of phi. Now power set of phi, now let's first write down all the subsets possible for this. Now since this is an empty set, we will not have any such kind of subsets. So therefore the only subsets that would be there would be this, or just we can write as phi. Now the set of all subsets would be the power set of this. So the answer of this would be set that contains the element phi, or the null set. Now next is we need to find power set of A. Now we just saw power set of phi is this. So therefore this P of phi we can write as set which contains the element phi. Now this would be equals to all the subsets which are possible for this set. Now, don't think of this being the empty set, just think of this being an element. So let's write all the subsets for this. So first subset would be phi itself, which is the empty set. Second would be this set itself, which is this one. Now, the set of all subsets will be the power set of this. Now similarly, if someone asks us what would be power set of power set of power set of phi, so that would be equals to power set of. So now think of this as the first element and think of this as the second element. So this answer to this would be very similar to this, where we will have the first subset being phi, second subset being this element phi, third subset being this element set phi, and then next being the set itself, which is phi comma set phi, the set. Now the set of all these subsets would be called the power set of this set, and so on. Now next is Venn diagram. It is a pictorial method to represent sets using circles and rectangles. Let's see an example. So let's say I have a set A which contains these elements and set B which contains these elements, and this is the universal set. So let me draw a circle that would represent set A, and let me draw another circle that would represent B. Now let's draw a rectangle that would denote a universal set U. Now let's start writing the elements of A. Now first of all, we notice that between A and B, between set A and set B, 6 is common. So therefore that element we can write here. Now remaining elements of A are 2, 4 and 8, and remaining elements of set B are 3 and 9. Now in universal set contains all these numbers, so all of them are included except the number 5 and the number 8 and the number 7. So this is how we pictorially denote the sets. Now we also know that we have something called union of sets. So A union is denoted by capital U. So A union B is all the elements of A as well as B. So that would be 2, 4, 8 as well as 6 and 3 and 9. Now similarly, we have something called intersection, which is denoted by this. So A intersection B equals to the common elements between A and B. So that's only 6. So A intersection B in this case is a singleton set. Now we just saw union of two sets and intersection of two sets. Now let's see them through Venn diagram. So let's say this is set A and this circle. So let's say this circle represents set A and this circle represents set B. So if someone asks pictorially what is A union B? So A union B would be all the elements in A as well as B, including the common elements. So meaning, if we would like to shade the region in which A union B lies, it would be this. So this whole region would be A union B, this entire region. Now A intersection B would be the elements which are common to both A and B, meaning the overlapping part. So it would be this region. Now what are disjoint sets? So as the name suggests, disjoint means they are not joint, meaning no overlapping part. So in such cases, if someone says that A and B are disjoint set, so that would imply that A intersection B would be null or phi. For example, if I draw a Venn diagram where this is set A and this is set B, so Clearly, there is no overlapping part, hence A and B would be called disjoint sets. These are also called mutually exclusive sets. Next is difference of sets. So, if someone asks what would be A minus B, so A minus B is not literal subtraction of B from A. What it means is all the elements of A except those elements which are also present in B, meaning all the elements of A except those elements which are in B, meaning everything except the overlapping part. So that would be something of this sort. So this is A minus B. Similarly, if someone asks what is B minus A, so that would be everything in B except the A part, which would be this region. Now next is symmetric difference of two sets. This is denoted by delta. So A delta B is the symmetric difference between A and B, and this is equals to A minus B union B minus A, meaning the union of A minus B and B minus A. So clearly the answer would be A minus B and simultaneously considering B minus A, meaning everything except A intersection B. Now next is complement of a set A. So that is denoted by A complement. That means everything except A, meaning if this circle represents the set A, then A complement would be everything outside A. So this would be the required region. Now let's do a few questions. So let's say someone asks us, so first is simplify A union bracket A intersection B. We can solve this through Venn diagram by drawing A and B and then proceeding step by step. So A intersection B would be this region. Now we need to take A union with the intersection part. So we need to take all the elements of A as well as elements of A intersection B. So the answer would be obviously this whole A. So essentially this would become A. Next is A intersection B intersection B. So that would be equals to what? So we will again use the Venn diagram. So first of all we'll find this. So this would be A intersection B. Next we would take intersection of this. So this was A and this was B. So next we will take intersection of A intersection B with B. So that would be this region itself. So the answer would be B and so on. Now next there are properties we must know. If A and B and C, if A, B and C are three given sets, then n of A union B would be equals to n of A plus n of B minus n of A intersection B. Next is n of A complement equals n of union n of universal set minus n of A. So this A dash means A complement, meaning number of elements in A complement would be equals to total number of elements in the universal set minus number of elements in A. Now similarly, it can be found out that n of A union B union C would be equals to NA plus NB plus NC minus n of A intersection B minus n of B intersection C minus n of C intersection A plus n of A intersection B intersection C. We will do a few questions based on this formula. N of A minus B, which is, so let's see this through Venn diagram. So let's say this is A and this is B and this is B. We want the number of elements in A minus B. Now A minus B is this. So what we need to do is we need to subtract this region from this. So the number of elements in A minus B would be equals to number of elements in A minus number of elements in A intersection B, and so on. So students, must memorize these formulas. Additionally, there's something called De Morgan's law. So this states that A complement union B complement is equals to A intersection B whole complement. Students are advised to remember this formula both this way as well as this way. Now similarly, you can review other formulas. Now similarly, students are advised to remember these formulas. So let's do few questions. In a class, 40% of students enrolled for maths and 70% enrolled for chemistry. Now, if 15% of students enrolled for both maths as well as chemistry, the question is what is the percentage of students who did not attend or who did not enroll for either of the two subjects? So, we see that there are two subjects under consideration. So, let there be two circles where this circle represents, this first circle denoted by A represents the students who enroll for math subject, and B be the circle which represents the students who enrolled for chemistry subject. Now it's given that total 40% enrolled for maths and 70% enrolled for chemistry. 15% enrolled for both maths as well as chemistry. So therefore, n of A intersection B would be 15%, meaning number of students who enrolled for both A as well as B, which is this common region, that would be 15. Now, the number of students who enrolled for maths or chemistry, which is n of A union B, that would be equals to n of A plus n of B minus n of A intersection B. Now this would be equals to n of A is number of students who enrolled for maths, so 40%, plus this would be 70% for chemistry minus 15%. So that would be equals to 95%. That means 95% students in the class enrolled for maths or chemistry. So therefore, the number of students who did not enroll for either of them, that would be A union B whole complement. So that would be equals to n of A, n of U minus n of A union B. So n of U is the total number of students, so that would be 100% minus 95%. So that would give us 5%. So 5% students in the class did not enroll for either of the two subjects. Now let's see this through Venn diagram. So we just saw that A intersection B is 15%. Now this part would represent the students who enrolled for maths but not for chemistry. So that would be 40% minus 15%. So that would come out to be 25%. Now similarly, this region represents the students who enrolled for chemistry but not for maths. So that would be 70 minus 15. That would give us 55%. If you add 55 and 15, so in total chemistry is 70%. The question is how many students in the class did not enroll for either of two subjects. So they're asking all the number of students which are present in this region, meaning outer to this whole. So this total would come out to be 95%. So therefore, the remaining would be 5%. Let's see another question. In a class of 40 students, each play one of the indoor games, which is either a chess or a table tennis or a Scrabble. Now out of which 18 play chess, 20 play Scrabble and 27 play table tennis. So let's say this circle denotes the set of students who play chess and it's denoted by C. Therefore, n of C would be equals to 18. Now, let's say this circle denotes the set of students who play table tennis. So that would be number of, let that be denoted by capital T. So therefore, n of T, meaning number of students playing table tennis would be 27. Similarly, this circle represents the number of students, the set of students playing Scrabble. So n of s would be equals to 20. Additionally, it's given that 7 play chess as well as Scrabble. So therefore, n of c intersection s would be equals to 7. Similarly, 12 play Scrabble and table tennis, and number of students who play chess as well as TT as well as Scrabble, meaning all three, is 4. Now we need to find the number of students who play only chess, who play chess and TT, who play chess TT but not Scrabble. So another thing that's given is that n of C union S union T, meaning number of students who play chess or Scrabble or table tennis is 40, which is the total number of students. Now we know the formula that n of C union S union T would be equals to n of C plus n of S plus n of T minus n of C intersection S minus n of S intersection T minus n of T intersection C plus n of C intersection S intersection T. So let's substitute the values. So we will get 40 equals to 18 plus 20 plus 27 minus 7 minus 12 minus n of T intersection C plus 4. So this would give us n of T intersection C as 10. So that means the number of students who play chess and TT is 10. Now let's fill this up in the Venn diagram. So number of students who play all three indoor games is 4. Number of students who play chess as well as Scrabble is 7. So therefore this whole region is 7. So this would be 7 minus 4, which is 3. Similarly, 12 play Scrabble and TT. So this whole region would be 12. So this would be 12 minus 4, which is 8. Now similarly, this whole region would be the number of students who play chess as well as TT, which is 10. So this would be 10 minus 4, 6. Now number of students who play chess is in total given as 18. So therefore, number of students, this region would denote the students who play chess only, and that would be 18 minus 6 minus 4 minus 3, which would be equals to 5. So therefore, there are 5 students who play only chess. The next is find the number of students who play chess, TT but not Scrabble. So meaning we want the number of students who play chess. So meaning they're asking the students who play chess, TT but not Scrabble. So they're asking this region. So for this we need to find this as well. So number of students who play TT is 27. So this would be 27 minus 6 minus 4 minus 8. That would give us 9. So therefore this region, the sum of students which belongs to this region is 5 plus 6 plus 9. So answer would be 5 plus 6 plus 9, which is equals to 20. So there are 20 students who play chess or TT but not Scrabble. Now next is Cartesian product of sets. Cartesian product of two sets A and B is denoted by A cross B, and it is the set of all ordered pair A comma B such that A belongs to capital A and such that A belongs to set A and B belongs to set B. So let's understand this by an example. So if A has elements 1, 2 and 3 and B has elements A and B, then A cross B would be equals to all the pairs which are possible from A to B, which is 1 comma A, 1 comma B, 1 comma 2 comma A, 2 comma B, 3 comma A, 3 comma B. So this would be A cross B, meaning all the ordered pairs which are possible from A to B. Now next is B cross A. So let's find B cross A. So here you need to understand
that we have to start from B and then map it with A. So this would give us A comma 1, A comma 2, A comma 3, B comma 1, B comma 2 and B comma 3. So note that A cross B is not in general equals to B cross A. Also note that number of elements in A is 3, meaning n of A is 3, n of B is 2. So number of elements in A cross B or B cross A would be 3 multiplied by 2, that is 6 elements, because that is the number of ordered pairs which you can make. So in general, if n of A is equals to P and n of B equals to Q, the number of elements in A cross B would be P into Q. Then there are few properties that students must note and memorize. Is A cross B union C would be equals to A cross B whole union A cross C whole. Similarly, this must be intersection part and not union, and this would also be. Now there are few properties that students must note and memorize, is that A cross B union C is equals to A cross B union, and this is A cross C. Now similarly, A cross B intersection C is equals to A cross B intersection A cross C. Third is A cross B minus C is equals to A cross B minus of A cross C, and so on. Students are advised to practice the exercise questions at home. Thank you.